All right. So yes, I'm here to talk to you about Tamagotchis and generators, and I'm really excited that Crystal went before me because she already explained some concepts that I'm going to go into in this talk as well. So again, hello, I'm Jen, software engineer based in New York. If you want to reach out to me on Twitter, my handle is girlcode. Definitely tweet at me. I post like a lot of cat pictures and stuff, but there's also some JavaScript usage. All right, how many of you had a Tamagotchi growing up? Oh yeah, I see a lot of hands. Sweet. Okay, so if you aren't familiar with them, Tamagotchis were really popular digital pets in the 1990s. So they looked like this. And when the game would start, an egg would appear and then hatch, and out would come your Tamagotchi as a baby. And you got to raise it from a baby to an adult. So you would clean up after it, you would play with it, you would feed it, it would beep at you when it needed things. It could get sick as well. And then you didn't actually know what type of Tamagotchi it was going to grow up to be as an adult. So that was the fun, surprise of the game. Now, when I was growing up, I nurtured a lot of Tamagotchis to adulthood. Some didn't make it. That's okay. But I really loved this game, and I just wanted to build my own web-based version of it. So my version of a Tamagotchi includes an SVG shell, the controls, which are just HTML divs to actually interact with the Tamagotchi. And then the game screen is actually built in Canvas. So if you aren't familiar with Canvas, to use it, we're going to query the DOM for Canvas. We're going to ask for the context. So in this case, we want 2D. And then to draw on the canvas, we're going to use context.drawImage. And we're going to pass it the image to draw, as well as some XY coordinates that I'm not going to get into right now. But that's going to draw the image to the screen. So at the bottom, you can see our Tamagotchi has been drawn to the screen. Now, for all the animations in this game, I used a sprite sheet. So below is the sprite to bounce the Tamagotchi. So if each frame of the sprite is at 200 pixels, then I need to draw the image at 0, then 200, and then 400 pixels. And so that's going to bounce the Tamagotchi up, and then I'd go back down to bounce the Tamagotchi down. Now, you'll notice that I'm doing context.clear between these drawings, and that's to avoid this situation. So if you don't clear the context between drawings, all the frames just draw on top of each other. All right, so as it's written now, this isn't going to work. It's actually drawing and clearing so quickly that you're only seeing the last frame of this. So that's not going to work. But I can delay the animation with set timeout. So I'm looking for this really old school, choppy, pixely animation like the original game. And I'm not going to build out a sprite sheet that is actually 60 frames, right? So I'm going to animate from frame 1 through 3 and then back to 2 and 1 for a full bounce using set timeout to do this, to delay the frame drawings. So this is going to work now. Aha, bouncing Tamagotchi. But I've created a problem here because now my animations are async. So how do I know when this animation is done? I have to know the actual amount of time that this is going to take. And that's in order to kick off another animation after this, or to not overwrite another animation, or have a weird long delay between them. And this just isn't sustainable for a game that's full of animations. What I want is to resolve an animation and then handle another animation. And this sounds a lot like a promise. Now, Crystal already talked about promises. But they represent an eventual value. So inside a promise, I can run the animation code, and then when it's done, I can resolve the promise. And since I can do a .then on the promise, I can use that to run an animation after it's complete. So for the first version of this game, that's what I did. I used promises for all the animations. I made a general purpose animate function that takes in a draw function and the milliseconds for the delay. Animate always returns a new promise. And inside that promise, an inner function is going to run the draw function. And we delegate resolving the promise to the draw function. If draw resolves the promise and returns true, we're done. Otherwise, setTimeout is called with the inner function, and another loop of this function occurs. So here we're going to actually use the animate function to create a bounce up animation. We're going to pass a function that draws the correct frame, clears the context, and increments the current frame count. When the current frame is greater than the frame count, the promise is resolved and we return true. So this would stop the function from setting another loop via setTimeout. And so now we can create a simple bounce function using our bounce up animation and a bounce down animation using the same animate function. And as you can see, our Tamagotchi is bouncing. Wonderful, beautiful. And so now that that's working, we can move on to creating the main game loop. So when you're not interacting with the Tamagotchi, it's going to show this idle animation. So it's going to bounce, it's going to move to the right, move to the left, keeps bouncing. It's so on and so forth. And to set up the main loop, we're going to create a loop function. We'll call the idle animation, and when that's complete, we call the loop function again. So it just continuously loops through. Okay, but I've created some more problems here. There's two main issues I noticed when using promises to build the animations. The first one is Venable Hell. So once upon a time, we used callbacks to handle async calls, and this created the dreaded triangle of doom, aka callback hell. And one of the issues I noticed when making this game was that promises really didn't alleviate callback hell. Like, you're still in hell, it's just a different looking hell. So the left side is a more realistic version of how these animations might work. So I might need to pass in information to functions or check information to make a decision, and this all gets just as unwieldy and as unmanageable as callback hell. And don't mistake me for hating promises. They're really great, but when you're doing more large-scale async work, the ease of promises really breaks down. And I noticed another larger issue with using promises for animations. So the point of the Tamagotchi is that the user can interact with it. I mean, the whole game is about interacting with the Tamagotchi. So at some point, I need to suspend the idle animation in favor of a user-generated event. So like feeding the Tamagotchi. So here I've added an array to hold pending events. The loop function checks if there are any pending events, and if there are, the handle event function is run, and the loop is terminated. So handle event is going to take the first event off the queue of events and run it. And when it's complete, we're going to restart the loop. If there's another event in the queue, handle event will get called again. Otherwise, we continue the loop until the next event. And so this didn't work. You can see I'm requesting to feed the Tamagotchi, but the feed animation is delayed until the idle animation completes its current loop. And that can be upwards of 7 to 8 seconds, so that's not going to work. What I need is to actually cancel the promise that runs the idle animation. Except you can't cancel a promise. Think of promises as unbreakable vows. Rest in peace, Snape. So you can throw errors in promises, and you can catch those errors, but you can't actually cancel a promise. All of the attach.then functions are going to fire. What I actually want is to pause an animation and yield to an event. And that sounds a lot like a generator. So generators are amazing because they're code that can be paused. So most of the code that you write is run to completion. Once it starts, there's no actually stopping it. Even if you're doing async work, you're throwing it onto the event loop, and it's going to come back around. You can't tell it to cancel itself and stop. You can't pause it. But with generators, you can pause and resume code. So let's take a look at them. So this is a generator. And I know it's a generator because of the asterisk next to the function keyword. That's actually all you need to do to turn a regular function into a generator function. And then inside, you'll notice the yield statement. So yield is a special keyword in generators that means pause. To use the generator, we're going to call it. And that's going to return to us the generator object. Now, on the generator object is a method called next. And that actually tells the generator to run until it encounters a yield statement. When that happens, it's going to return to you an object with a value key and a done key. So if there's a value to the right of the yield statement, it will be passed via the value key. And then done provides the status of the generator. Is it done, true, or false? So in this case, this generator is not done, so we're getting false. Now, you don't need to yield values. Yield is just a keyword that means pause. So you don't need to return a value with it. So in that case, yielding no value is going to return undefined. And as you can see, we're still not done, done, false. So now we're calling next again. We're yielding 3, so the value is 3, and done is false. But done is still false, right? Like we haven't actually finished yet. It's on the next call that now we're actually truly done. You can also pass values into the generator's next function. And so here we're passing 2 into the second next function. And this seems a little odd at first, like why aren't we doing this on the first call to next? But when you call next, what you're saying is, hey, generator, do whatever you need to do until you encounter a yield statement. So in this case, there's actually nothing for the generator to do before the first yield statement. So when next is called, it sees that yield statement, and it's going to pause there. And the yield statement has no value associated with it, so the value is undefined. On the second next call, we pass in a value. And that value is going to take the place of yield. And now, because we've called next and we've said, hey, do whatever you need to do until you see a yield statement, the value is now being assigned to the variable num. The generator runs until the next statement, and this time we do have a value yielded back, 2 plus num, or 4. On the next call, the generator yields 4 plus num, or 6. Then it's done, no more yield statements. You can also create an infinite generator. So how many of you use while loops? Yeah, just a handful of you, like in production. Very few, okay. Generally, we don't. I mean, when I was learning while loops, obviously what I did was crash my browser. I think we all did. So in this example, like first we're going to pass in an initial value into the generator function, and this is going to avoid relying on next to set the initial value of num. And then you're going to see the while loop, right? And we're doing while true. So this should crash my computer. Like this is an infinite loop and should crash my browser, and I'll be annoyed with myself. But actually, because generators can pause, it's actually pausing the while loop. So it's not going to cause a crash. The yield statement's going to pause it for us, and it's only going to resume again when we call next. And so as long as you keep calling next, this is going to keep running. So this is going to be an infinite generator, but you don't have to worry about overloading the event loop with the while loop, because generators can pause. Now, you can also run a generator from inside of another generator. And to do that, you're going to use the yield asterisk expression. I'm going to call it yield star because it's just a little bit easier to say. But to illustrate this, I have a generator function called outer and a generator function called inner. And you'll notice that outer is calling inner with the yield star expression. So same as before, we're going to call outer, and that's going to return to us the generator object. So the first time we call next, what we expect to happen, happens. The generator runs until it encounters a yield statement. So this runs, encounters yield, and the value to the right, 1, is passed back as the value. But when we call next again, the generator isn't going to pause at the yield star. You can see it's pausing at the first yield statement in the inner generator. And the value being returned isn't the generator itself, but the value A from the inner generator. So yield star is a delegate. So when you call next and it encounters a yield star expression, it delegates the generator to the right of that expression. And it will continue to do so as you call next until that generator is complete. So when we call next again, the inner generator isn't done yet. So now the value is B. Now the inner generator is complete, and so we move on to the next yield statement in the outer function. And in addition to being paused, generators can be canceled, and you can do this one of two ways. So the first is with a return statement. So this generator, because it's using a while true, it should run for as long as I call the next method. But instead, when this generator encounters the return statement, it's going to cancel itself. So you can see that done is now true. And it doesn't matter how many times I call next, this generator is done. And you can also cancel a generator from outside of itself. So here again, the generator should be infinite. But when I call the return method on it, it cancels the generator. And this is really interesting, that you can cancel a generator from within or outside, because you can only resume the generator from outside of it. So generators are paused via yield and restarted via next. But a generator cannot call next on itself. If I never call next on this generator, it will never yield 2. It stays paused. And this is something I really struggled with when I was converting the game from promises to generators, because who runs the generator? So if control happens outside, like something has to be pulling the strings. Like how do you know to keep calling .next on something, or how many yield statements there are in something? And so this is where coroutines come into play. So coroutines are a general control structure where control flow is cooperatively passed between two different routines. I like to think of coroutines as cooperative partners. Because the generator can't resume itself, you need a cooperative partner to help out. So this function is a basic example of a coroutine. It's going to take in a generator, and it's going to call it, which returns the generator object. The inner function, next response, calls the generator's next method. This starts the generator, which will run until it encounters a yield statement. At this time, the generator returns an object with the value key and the done key. Next response evaluates whether the generator is done or not, calls itself, and if not, it calls itself with the value from the generator's response. And this loop continues until the generator is done. So the coroutine is the cooperative partner to the generator. The coroutine function passes control to the generator, and when the generator pauses, control is yielded back to the coroutine. And these two functions cooperatively pass control until completion. So now I can rewrite the bounce animation as a generator and use a coroutine to run it. Except you'll notice that this code suffers from the same issue I had in the beginning. The animation still happens too quickly. I still actually need set timeout, and I actually still need promises. But my generator doesn't care if I'm using promises. It's not going to wait for each individual promise to resolve and then resume itself. Like, it can't resume itself. But a cooperative partner could. So I can amend my coroutine to handle async requests. Instead of calling next response, we'll call a handle async function. We'll pass it the value of the generator's response, which is a promise. And now we can prevent the generator from resuming until the promise is resolved. When it's resolved, we'll call next response, which will resume the generator. So with this amended coroutine, these functions are now equivalent. So previously, we chained promises together for the animation, and now we can yield promises, and our cooperative partner, the coroutine, will handle resuming the generator when the promise is resolved. So you can do more than yield promises. You can yield all sorts of async things like callback functions and generators themselves and more. And there's a really great library called Co if you want to play around with that. I really highly recommend it. Coroutines are very, very powerful. And the reason they're so powerful is that they allow you to think sequentially about async code. Because the coroutine is your cooperative partner in handling the messy business of chaining and dealing with async code for you in the background, you can write your code as if it ran sequentially. So for the second version of this game, I rewrote all the animations with promises and generators. So what you're seeing here is actually the same idle animation, but with generators and promises, and run by a coroutine. And I had two goals with this rewrite. I wanted to be able to pause animations, and I wanted to take advantage of thinking sequentially about async code. So to do that, I started with rewriting the function that delays the animation. So this is our async function, and it doesn't need to hold the animation itself. It just needs to delay with a promise. That's its sole responsibility. So when this function is called, it returns a new promise and resolves that when the timeout is complete. I also broke out the context clearing into its own function and the drawing of the image into its own function. And now we can combine these new functions to replace the previous animation function, and we can do so inside a generator. So we'll clear whatever was previously on the canvas and then draw the new frame. And those can occur synchronously. We'll yield the delay. That's the asynchronous part of this function. But because we're handing it off to the coroutine, our cooperative partner, this looks and feels very synchronous. The coroutine will handle the resolve promise when the timeout completes. And so here's our draw frame generator in use. This dislike animation draws 2 frames, and because draw frame is a generator, we're using yield star to delegate yield calls to it. So for each call and draw frame, we're clearing the context, drawing the frame, and then delaying. And then this is what the dislike animation looks like. You can see it's a very unhappy Tamagotchi, just really pissed. Okay, and now we can rewrite also the main game loop and take advantage of canceling the generator. So our loop generator function will be run by a coroutine, so we can rely on it to handle any values yielded to it. We'll create a variable to save the status of the generator, done or not, and we'll preset the animation to idle. We'll use a while loop to create a never-ending generator. So this way, the game loop is going to continue forever. If we have a pending user event, we'll cancel the current animation and delegate to the event using yield star. And whatever the event yields will be passed to the coroutine. Otherwise, a second while loop will handle running the animation. A while loop inside a while loop. I want you to understand that this is nuts. As long as the animation is not complete and there are no pending events, this loop will yield the generator's values to the coroutine to handle. And these are promises, so the coroutine is going to handle the chaining. But if the animation is done, or there is a pending user event, the loop is going to terminate, stopping the animation generator from running again. And we'll reassign animation to the idle generator to start from fresh, and we'll reset done to false. And on the next iteration of this while loop, pending will be true, and we'll handle the user event instead. So this is the generator function for the feed action. It evaluates if the Tamagotchi is hungry or not. If it's not, it delegates future calls to the dislike generator, which will run the dislike animation. Otherwise, we're going to decrease the hunger count and use yield star. We're going to delegate to the eat generator that runs that animation. All right, so will this work? All right, so we're idling. I'm going to say, yeah, I want to feed you. I'm going to feed you a burger. He's eating. All right, so the idle animation canceled. We're going to do it again. But this time, I'm going to feed him candy in a second. Because, you know, a well-balanced meal. There we go. Cool. All right. He seems fine. So idle animation keeps running again. All right, let's feed him one more time, because I think maybe he's still hungry. Nah, he's mad. He doesn't like that. All right, so that's all for me. If you want to check out the code for this, there's the link to the repository for it. And